So today we're going to talk about significant figures, also called significant digits. And we've already talked about how in chemistry we use measurements and we don't use numbers. And we recognize measurements because they have units after them. But because they're measurements, we have to treat them with the same degree of reliability as the instruments that did the measuring. And so we treat them a little bit differently than numbers. So get out a piece of paper, a pencil. You're going to need to write these rules down. You're going to need to know them because these are the rules that are going to dictate how we round our answers when we do chemical calculations. Let's get started. So because numbers used in chemistry are measurements, the calculated answers are only as good as the measurements they come from. And anytime we do a calculation, we have to be aware that those answers reflect the degree of reliability as those tools that we used. So the first thing we're going to do is talk about how to recognize significant figures in a measurement. And keep in mind, we're looking at the digits that are significant to the measurement. They may or may not be significant to the number, but they are a significant part of the measurement. Number one, rule one, any number other than 0 is significant. So the example here is 96.2 grams. 9 is significant, the 6 and the 2, they're all significant. So we would say that this measurement has 3 significant figures, or sig figs for short. The rest of these rules deal with zeros. As you can tell from this rule, the issue aren't the digits that aren't 0, it's the 0 itself. So let's move on to rule number 2. Rule number 2, zeros between significant figures are significant. So after you've written that down, and if you need to pause this to do that, then feel free to pause this at any time because you need to write these down. Take a look at the example, 5.029 meters. The 5, the 2, and the 9 are significant because they are non-zeros. The 0, because it's between the 5 and the 2, becomes significant as well. So we would say that this measurement has 4 significant figures. This is where it gets a little trickier. Rule number 3. One or more final zeros after a decimal are significant. So for example, in the measurement 82.0 meters, that 0 is a final zero after a decimal. It is significant to the measurement. Now this is where it gets a little confusing with numbers because whether you said 82 or 82.0, that's the same number. But it's really what we're communicating about this measurement. We're saying that that 0 is our final estimated digit part of that measurement, not the 2. And so we take it out to that 0.0 to say that that is the degree of reliability of that measurement. Here's another example, 0.1230 meters. In this case, you have a decimal place, and that final 0 after the decimal place, that 0 that's after the 3, is a significant digit. It's a significant part of the measurement. It is telling you that that measurement went all the way out to that 4th decimal place. And of course, that leading 0 before is just holding that decimal place in place. Okay, so that's when zeros are significant. Now let's take a look at when zeros are not significant. And for that, we look at rule number 4. Rule number 4. Zeros used for spacing the decimal point are not significant. They're only placeholders. For example, in the measurement 7,000 milliliters, the 7 is the only significant digit. Those zeros are merely holding the 7 in that place. That 7 is the estimated digit. Whatever tool measured this really it probably was just between 0 and 1 liter. And you're looking at, well, it's over half a liter, so it must be about 7,000 milliliters. And so those 3 zeros are not significant. They're merely placeholders. And that's where this is different from a number. It's significant to the number, but it's not significant to the measurement. Here's another example. 0.000783 milliliters. So now we have zeros after the decimal place, just like we did in rule number 3. But the difference is these are leading zeros. These are zeros that are before the measurement begins. Those are placeholder zeros. They are not zeros that are significant to the measurement. So that we would say that this has 3 significant figures, the 7, the 8, and the 3. Now, this can be a little confusing when you're starting out using significant digits, when to recognize when those zeros are significant or not. So I do have a suggestion for helping you recognize when zeros are significant or not. And my suggestion is to use scientific notation, because one of the things that scientific notation does well, it doesn't only show us large numbers and small numbers, it also takes away any insignificant zeros. Here's what I mean. If you take that 7,000 milliliters and you turn it into scientific notation, it becomes 7 times 10 to the third. And that 7, that significant digit is on the left side of the expression. And that's going to be the case. If scientific notation is done correctly, the left side of the expression should always be significant digits, and they should only ever be significant digits. And you can see that those zeros just sort of melt away because they're merely holding the place. By the same token, 0.000783 in scientific notation, because 7.83 times 10 to the negative fourth. So those zeros were merely there to hold that decimal place and hold the placeholder for that number, not significant to the measurement. The 7 and the 8 and the 3 are significant. Here are a couple more examples. 220 grams written in scientific notation would be 2.2 times 10 to the second. There's that insignificant zero goes away. By the same token, let's say the measurement had been 220.00. Now, in this case, you have final zeros after the decimal place, which are significant, and that zero that wasn't significant is now significant because it's between significant digits. So if we were to write this correctly in scientific notation, we would keep the zeros. It would be 2.2000 times 10 to the second, showing that there are actually 5 significant digits in this particular measurement. So use scientific notation to help you out. It can also control your significant digits. You will find yourself in a situation where maybe you need to say 100. The answer is 100, and you need to show that that 100 has 2 significant digits. Well, the problem is the measurement 100 only has 1 significant digit, 1. So to show 2 significant digits, say in that example, you would call that 1.0 times 10 to the second. So scientific notation also allows you to control significant digits. All right. So that's how we recognize them. The first skill with significant digits is being able to recognize significant digits in measurements. We're going to jump to the next skill, actually, which is rounding measurements to control the number of significant digits we have, because this is what you're going to do. Ultimately, when you do your calculations, you're going to need to round your final answer. So let's do a little bit of that practicing. 4,555 grams. Okay, that has 4 significant digits, and we want to round it to 3. So to do that, we would keep the 4, keep the first 5, and then round that second 5. And because of the 5, we would round it up. So this would become 456. And because it's the 4 is in the thousands place, we need to maintain that. So we wouldn't just drop that final digit. We would actually add that insignificant 0 at the end. So this would be 4,560 grams, with that 0 being an insignificant 0. 2.333 grams. So in this case, 3 significant digits, we would drop that final 3, 2.33 grams. Now in this case, we did not add a final 0, because if we had, that would have been a final 0 after a decimal place. It would have been significant. And so in this case, because it's after the decimal, we would just drop that. Similarly, here's 65.1 meters. Of course, that is 3 significant digits, so there's really no rounding necessary. 1.2345. Here, similarly, you've got 1.2. You need to round that 3. Now, be careful not to overround. You know, you've got 45. The 5 isn't going to round the 4 up to a 5, and then that 3 up. That's overrounding. In this case, I would just look at that 3. I'd look at that 4, 5. it would round down and drop those digits. It would be 1.23 meters. 12.345, similarly, drop that 4.5, 12.3 meters in this case. 2,342, this is similar to the first example. 2,300, and that 4 is where you would round. In this case, you'd round down. You want to maintain the placeholders here, so this would be 2,340 meters in this case. 10,476. So in this measurement, the 0 is significant because it's between significant digits. So what we're rounding here, we're going to keep that 10,000, and we're going to round that 476 up to 500. So rounded to 3 significant digits, you've got 10,500 meters, which is interesting because here you have an example where you have zeros that are significant and insignificant in the same measurement. The 0 between the 1 and the 5 is significant, but those zeros that are part of the 500, they're not final zeros after a decimal place. They're merely placeholders, so those would be insignificant. Identifying significant figures becomes a matter of correctly rounding your answers to calculations using measurements. So then we're going to move on to the next step, which are the calculations, and looking at the rules for how we make sure that the reliability of these measurements is maintained when we're doing calculations. So there's 2 more rules. There's going to be a rule for multiplication and division and a rule for addition, subtraction. Let's start with addition and subtraction. Write this rule down. You're going to round your answer to the same number of decimal places as the measurement with fewest decimal places. Okay, so first thing you need to know about calculations is you're going to calculate exactly the same way. You're not going to change anything you do. Don't round anything. Use the measurements as they were given to you. The issue is, what do you do when you get that answer? And, you know, I typically get the question early in the year, oh, Ms. Menier, you wanted us to round to 1 decimal place or 2 decimal places. No. You need to follow the rule for the operations you're doing. And we want to be consistent with the measurement that has the lowest level of reliability. So in this case, we have to round to be consistent with the measurement with the fewest decimal places. Here's an example. And grab a calculator for this. Once you've written the rule down, let's go ahead and do this calculation together. 9.88 plus 1.2. And just add them up as written. What'd you get? I got 11.08. So that's the answer, but that's not the answer I'm going to report, because now I have to look back at the measurements it came from, and I see that 9.88 has 2 decimal places and the 1.2 has 1. So my answer should only have 1 decimal place. So even though the calculator said 11.08, I'm going to round that to 11.1 to be consistent with the measurement that had the fewest decimal places. Here's another example. 90 minus 43.1. Go ahead and do that calculation on your calculator. What did you get? I got 46.9. Okay. So in this case, I go back, I look at the measurement with the fewest number of decimal places, and it's obviously the 90, but here's the other issue with the 90. The 90 has an insignificant 0 in the ones place, so it actually doesn't even have that digit there. It actually starts at the tens place, and that's what I need to round to. And this one's a little bit uncomfortable because you might look at your 46.9 and think, oh, I'll round that to 47. No decimal places. No. That 7 would give you a digit in the ones place, and 90 doesn't have a digit in the ones place. Therefore, this would have to be rounded all the way to 50 seconds. And that seems a little extreme. It seems a little crazy to round 46.9 all the way to 50. But the problem with this calculation comes from the problem with the measurement to begin with. That 90 seconds is a fairly unreliable measurement. And so really it just tells you that in order to get reliable answers from your calculations, you really need to start with reliable measurements. And that's where you in lab comes to play. You need to make sure that you are getting the correct digits to begin with. All right, let's move on to the last rule. The rule for multiplication and division, which is slightly different than addition and subtraction. In this case, you're going to do your multiplication division like you always have, but when you get your answer, you're going to round your answer to the same number of significant digits as the measurement with the smallest number of significant digits. Okay, so you're not looking at decimal places here, you're looking at the total number of significant digits. So let's take a look at this example. 36.5 times 2.1. And I get 76.65. Okay, so that answer has 4 significant digits. When I look back at this problem, 36.5 has 3 significant digits, 2.1 has 2 significant digits. So I need to be consistent with the measurement with the fewest number of significant digits, which is the 2.1. So my answer can only have 2 significant digits. So I'm going to take that 76.65 and round it to 77. Okay. For my last example, it just sort of brings home this idea that you need to make sure your measurements are good measurements based on the instruments you've been given. Let's say, for example, that I give you a ruler and a little piece of paper, and I ask you to measure the edges of the paper, and you take the ruler and you measure one side to be 3 centimeters and one side to be 4 centimeters. Now, I'll tell you right now that there's not a ruler that we have that would give you just one significant digit. They're going to give you 3 significant digits. They usually go out to 1 or 2. They should go out to 2 decimal places. So not great measurements. And when you tell me it's 3 and 4 and I ask you to find the area, well, 3 times 4 would be 12. But the problem is 12 has 2 significant digits. And so with measurements like 3 and 4, you would have to say that the area is 10 centimeters squared. And you kind of look at it and say, no, 3 times 4, you can't say it's 10. Well, you've got to go back to those measurements and you've got to make sure that you had the correct number of significant figures in your measurement to begin with. And you probably did it. And this is going to be very important when we do something like read a graduated cylinder. And you see the graduated cylinder has 20 milliliters in it. And well, that 20 milliliters is only one significant digit. Are you sure it's not 20.1 or 19.8 milliliters? You need to read it to the level of reliability of the instrument. If you do that, if you have good measurements, you'll get good answers. But either way, you need to follow the rules for significant digits. And these rules won't go away. I know they're kind of hard to follow at first, but they are something that we do with every calculation all year long. I'll certainly help you with checking over those as need be, but they are part of the calculations that we do. So practice your significant digits, practice rounding when you get your answers, and make sure you're following the rules for addition, subtraction, and multiplication and division.